Okay, let's finish up this 4.3, Cramer's rule and some applications of determinants. We left off having reviewed our little protocol for computing determinants using row reduction. And we stated Cramer's rule, a computationally complex, computationally intense way to solve a system of n equations and n unknowns. And even then we required that there exists a unique solution to apply this Cramer's rule thing. It worked out just fine for 2 equations and 2 unknowns. Larger than that, it's going to be unwieldy. So let's continue on. The new topic is we're going to introduce a new matrix operation which produces a new n by n matrix based on a given n by n matrix. This new matrix, it turns out, is related to A inverse. We can use this new matrix. It's called the adjoint. We can use the adjoint of a matrix to find the inverse of a matrix, but the adjoint of a matrix is going to involve determinants. And you know how lengthy that can be. And you already have a way to find the inverse of a matrix. So maybe using the technique we're going to have to actually compute an inverse, that ain't a good idea. You've got a perfectly decent way to find the inverse of a matrix. Take a given matrix, augment it with the identity, and go to town with row reduction. There's reasons to explore these topics. Actually computing inverses, that's not a real application we would want to do. All right, recall these little primed A sub ij's. A sub ij prime was a cofactor of a matrix A from the last section or two. It was plus or minus the determinant of the minor matrix associated with the element A sub ij. It was -1 to the I plus j times the determinant of the minor matrix, capital A sub ij. We did extensive amounts of that stuff. Well, you're going to get a little more practice with that. For definition, for an n by n matrix A with the usual entries, lowercase a sub ij's, define the adjoint of A as the adjoint of A is the transpose of the matrix A prime, where the matrix A prime is the matrix of cofactors of matrix A. So we'll compute all these little A sub ij primes, all these little cofactors, put them into a matrix. A11 prime goes into the 1,1 entry of this matrix, and so forth. So we'll make a matrix of cofactors, call that A prime. The transpose of that matrix of cofactors, that's the adjoint of matrix A. So this doesn't involve anything we haven't done before. We've found minor matrices, we've found cofactors, we've done transposes, we've just never linked them all together as we're doing here. So let's compute an adjoint for a matrix, hopefully not a very big matrix. Let's look at number 18 in the supplements. Here's a 3x3 matrix. Find the adjoint. Okay, so let's see. We got to find a bunch of cofactors. We got to find 9 cofactors because it's a matrix with 9 entries. A11 through A sub 3. Okay, off we go. We need A11 prime. Okay, that'd be the cofactor associated with a 1,1 entry in matrix A. That would be -1 to the 1 plus 1 power. -1 squared is +1. Yeah, we'll start with a positive. We'll eliminate the row and column as before, containing this 1,1 entry. That'll leave us with a little minor matrix, 1, -2, 1, 4, as given here. So we'll have positive determinant to this minor matrix. That would be 1 times 4 minus 2 times 1. It'd be 4 plus 2 is 6. There's that first cofactor. Move to the 0. Now we're not calculating determinants, we're calculating adjoints. There's a 0 here. I'm sure all the appreciate the presence of the zero somewhere in the future, but we still got to compute this cofactor, a sub 1, 2 prime. We're doing something a little different from when I was thrilled to see zeros before. So we'll compute a 1, 2 prime. We'll eliminate the row and column containing the 1, 2 entry, the 0. That'll leave us with the minor matrix 4, negative 2, negative 5, 4, as given here. Oh, we'll have negative 1 to the 1 plus 2 power. Negative 1 cubed is negative, so we'll have a negative out front, times the determinant of that minor matrix. We'll move to the 1, 3 position, do the same type thing, as well as for the other 6 positions. So we need these 9 cofactors to find the adjoint of matrix A. I've been predicting, because of that powers of negative 1, we're looking at kind of a checkerboard of negative signs. Notice the coefficients are going positive, negative, positive, negative, positive, negative, positive, negative, positive, reading along the rows. You read along the columns, they alternate in sign as well. Positive, negative, positive, negative, positive, negative, positive, negative, positive. So you've got this kind of little checkerboard of plus and minus signs. In the upper left-hand corner, we've got a positive, and then it alternates in signs as we move from left to right or from top to bottom. So that's all caused by that negative 1 to the I plus j thing in the computation of cofactors. And if I go all the way back to when we first defined the determinant of a 3 by 3 matrix, there was this negative sign that popped up. Same thing happened when we did cross products of vectors. So a little negative sign popped up in front of the k component. I'm sorry, the j component, the middle component. It's because of those powers of negative 1. It was following this pattern of positive, negative, positive. This is just that pattern kind of writ large. Okay, so do your arithmetic. It's nothing hard. It's just bookkeeping, really. And we'll produce all these cofactors. So we'll put those cofactors into a matrix. We denoted that matrix A prime. So we get matrix A prime, the matrix of cofactors, to be these entries, 6, negative 6, 9, 6, negative 6, 9, and so forth. Now that ain't the adjoint. That's the A prime matrix. The adjoint of matrix A was the transpose of this A prime matrix. Okay, so we've got the A prime matrix reproduced here from the previous slide. Take a transpose of it. All right, interchange the rows and columns. Maybe been a little while since we've done a transpose, but you take the first row of A prime and that becomes the first column of A prime transpose. Second row becomes a second column. Third row becomes a third column. We've taken a transpose here. And that's the adjoint of the original matrix A. What we can use it for, well, we can use it for something and we will, but we're not there just yet. So back to the notes. Some properties of the adjoint, or a property of the adjoint is, suppose A is an n by n matrix, then they claim, proofs in the supplemental notes, let's not bother in the video. They claim that the adjoint of A, which is also an n by n matrix, times matrix A, okay, so that matrix product really makes sense. They're both square matrices of the same size. Adjoint of A times A equals A times the adjoint of A. So there's some commutativity, which we in general don't have, but apparently have here. And the claim is that product is the determinant of A times the identity matrix. So what this right-hand thing would be an n by n square matrix, zeros below the diagonal, zeros above the diagonal, and that number, determinant of A, whatever that is, along the diagonal. Okay, so we've got a scalar multiple of the identity matrix, and we got a product of matrices here related to the identity matrix. So this theorem 4.6 isn't quite the punchline in terms of adjoints. It's this corollary, 4.3.8 that is. If A is an n by n matrix and its determinant is non-zero, what do you know about matrices with non-zero determinants? They're invertible, as we stated at some point in the, I think, the previous section. So we had A is invertible if and only if the determinant of A is non-zero. So if we assume the determinant is non-zero, then we know from previous experience that A is an invertible matrix. And here's a formula for the inverse of matrix A in terms of adjoints. The claim is A inverse is 1 over the determinant of A times the adjoint of A. Why is that? Well, if you'll look back upstairs in the theorem, we've got matrix A times the adjoint of A on the left or right equals a determinant of A times matrix I. Well, if we were to divide by this scalar, determinant of A, it's just the determinant of A part that I want, divide both sides of this equation by the determinant of A. It's just a number. Determinant of A is just a number. The other stuff is matrices. Then we'd have 1 over the determinant of A times the adjoint of A times A equals, determinant will have been divided out, the identity matrix. So we've got a product of two matrices in either order that produces the identity matrix. Those matrices are inverses of each other. That is, 1 over determinant of A times the adjoint of A is the inverse matrix of matrix A. Divide by determinant of A, take that scalar, stick it inside the adjoint of A, and that will produce a matrix. We multiply by matrix A to produce the identity. That's an inverse matrix. Is this an efficient way to find inverses? No, because it involves the determinant of matrix A. Oh yeah, and the adjoint, dude, that involves n squared determinants. Determinants of n minus 1 by n minus 1 matrices at least, but that's a bunch of determinants. So this isn't an efficient way to find the inverse of a matrix. You've got an efficient way to find the inverse of a matrix as dealt with in chapter 1. Let's illustrate it. Though we left off, having done this number 18, we were given a matrix and we found its adjoint. Well, given that information, now we could find the inverse of matrix A using the adjoint, since we already know the adjoint. I think we still need one more piece of information. Properties of the adjoint, let's skip that, and let's do this number 18, where you're asked to find the inverse of matrix A using the adjoint. This is the same matrix we just looked at. It's a continuation of problem 18. We need the determinant of matrix A. We, in finding the adjoint of A, found 9 determinants. None of them were matrix A. They were minor matrices of matrix A. So we still need the determinant of matrix A. It's a 3 by 3. We'll just take the definition of determinant of a 3 by 3 that we initially had by expanding along the first row. It takes advantage of this 0. You got a better idea? I am rather attracted to these two 1s. We could do some row operations and change one of these 1s to a 0, and that'd leave us with 2 zeros and a 1 in the second column. We could do that, and that'd probably simplify the arithmetic. So maybe that is a better idea. But anyhow, the determinant of matrix A is, looks like it's 45. There's the computation. So we can find from that corollary the inverse of matrix A by taking the adjoint of matrix A and multiplying it by the scalar 1 over the determinant of A. Determinant of A was 45, so we'll get 1 over 45. The adjoint, this is the result from the previous example. So there's A inverse. I can clean it up a little bit. All these entries are multiples of 3. So we could divide a scalar multiple of 3 out of that matrix. Then we'd have 3 over 45, which is 1 over 15. So here's a slightly simpler version of the inverse of matrix A. It's still got that fraction in it. Yeah, when I saw the determinant of A wasn't 1, say, there was a very good chance we were going to introduce fractions. In hindsight, If you want to know if the inverse of a matrix has fractions in it, one thing you could do is take the determinant. If the determinant's plus or minus 1, there won't be any fractions in the inverse of the matrix. Of course, that's not an if and only if result. We could have had a determinant of 3 here, and that would have been nice. We would have still had all integers involved because all of these are a multiple of 3. But if the determinant is plus or minus 1, there won't be any fractions in A inverse. I can't give you a more general result than that. It depends on the specific matrix. So there's an illustration of finding the inverse of a matrix using adjoints. Let's look at this one as well, which says, given the inverse of a matrix, given A inverse is A, B, C, D, it's given here, and the determinant of A inverse is 3, find matrix A. All right, so in a sense, they've given us 2 out of 3 pieces of information. They've given us the inverse of a matrix, the determinant of the inverse, and they're asking us to find the matrix A itself. Well, we know how to relate the inverse to adjoints and determinants, given what we just saw. Now, they haven't given us the determinant of A. They've given us the determinant of A inverse, close enough, if you'll recall some of the things we know about determinants of inverses of matrices. But let's use what we know. What we know is A inverse is the adjoint of A times 1 over the determinant of A. Determinant of A. Well, the determinant of A inverse is 1 over the determinant of A. We said this in the notes. It's exercise 4.2.31, I guess. Follows from the product rule of determinants. But determinant of A inverse is 1 over the determinant of A. So the determinant of A is 1 over the inverse, 1 over the determinant of A inverse. Determinant of A inverse is 3, so the determinant of A itself is 1 over 3. So we get that reciprocal relationship between the determinant of a matrix and its inverse. They gave us the determinant of the inverse. We can find the determinant of the original matrix. So we got determinant of A. So if I peek back up here to this formula, they gave us A inverse. We now know the determinant of A, adjoint of A. So we don't know the adjoint of A, but I'll bet we could do some manipulations to find the adjoint of A. Matrix A, the question is, find matrix A, say has entries A11 through A22, the usual kind of thing. And we need to find all these A11, A12, A21, A22 things. That would answer the question. Well, we got this formula involving the adjoint of A. So let's take this expression for matrix A and let's find the adjoint in terms of these double subscripted A's. And I think from there, we can actually find matrix A. So let's find the minors. The cofactors for this matrix. A11 prime for this matrix, we take -1 to the 1 plus 1. You know, you're going to get positive, negative, negative, positive when I go through the little minors because of the checkerboard pattern mentioned earlier. We'd eliminate the row and column containing this entry. That just leave A22. So for A11 prime, we get positive A sub 22. For A12 prime, you know, we'll get a negative coefficient. We'll eliminate the row and column containing that. That'll leave us with A21. So A12 prime is negative A sub 21. Think in terms of eliminating rows and columns where these entries come from. Otherwise, it's just a jumble of double subscripts. A21, I go to the A21 entry. I know we'll have a negative out front because of the alternating plus and minus stuff. You don't like that? -1 to the 2 plus 1 based on those indices, -1 cubed, negative. And we'll eliminate the row and column containing the 2, 1 entry. That leaves us with the 1, 2 entry. So we get A21 prime is negative A12. Similarly, A22 prime be positive given the location. Eliminate row and column. It'll be the A11 entry, positive A11. Okay, so we found the cofactors of all the entries of matrix A, so we can find them in matrix A prime. The 1, 1 entry, stick with me there. The 1, 1 entry of this matrix would be A11 prime. A11 prime equals lowercase a sub 2, 2. So we get an A22 here. This would be A12 prime. A12 prime, it's the 1, 2 entry of A prime. In terms of the elements of matrix A is negative A21. So we get a negative A21 here. This would be the 2, 1 entry of A prime. It would be A sub 2, 1 prime. A sub 2, 1 prime is negative A12. Negative A12 goes here. This would be A22 prime. A22 prime equals A1, A11, and A11 goes here. So there's the matrix A prime in terms of the entries of matrix A. We need the adjoint. Okay, now I got to transpose this thing. If you do it one little step at a time, it should make sense, but it is a lot of moving parts. So we'll transpose this to get the adjoint of A. So the adjoint of A is A prime transpose. All right, that'll just interchange these two entries here. So we get this matrix here. Notice the negative A12 entry down here has gone above the diagonal when we did the transpose. Similarly, we've got the negative A sub 2, 1 entry down here. All right, so there's the adjoint. We know from the corollary that the adjoint of A equals the determinant of A times A inverse. It's this little formula where we've cross multiplied by the determinant of A. We know the determinant of A, that's right here, that was 1/3, 1/3. We know A inverse, they gave us A inverse, it's one of the pieces they gave us. So that allows us to express that adjoint also as 1/3 times ABCD, determinant of A times A inverse, given in terms of the A's, B's, C's, and D's. All right, well now, if we'll equate this with this, probably need to take that 1/3 inside, then we can find A sub 2, 2. This entry, A22, will equal A over 3. A22 equals A divided by 3. This negative A sub 1, 2 will be B over 3. Well, if negative A sub 1, 2 is B over 3, then A sub 1, 2 itself is negative B over 3. This thing here, negative A sub 2, 1, must equal the corresponding entry over here, which is C over 3. Negative A sub 2, 1 equals C over 3, so A sub 2, 1 itself, cross multiplying, is negative C over 3. This entry here, A11, must be D over 3. A11 equals D over 3. So we've got the information to find all 4 of the double subscripted A's. It was a little sideways how we got here, but it's correct. And now we can take these 4 things, these are the entries of matrix A, plug them into matrix A, finally some sane subscripts, nothing's jumbled up in matrix A, so A11 was D over 3, A12 was negative B over 3, and so forth for the other 2. And there's matrix A in terms of the A's, B's, and C's that we were originally given. All right, so that one's a little bit tricky. It really is just computational. It looks funny because you're taking these double subscripted A's and moving them around, and they're picking up negative signs because of the cofactor stuff. But there's an illustration of a manipulation involving A inverse and adjoints. An additional little comment, if we just had a 2x2 matrix, A, B, C, D, then the adjoint of A can be computed as D, negative B, negative C, A. What's happened is you've interchanged these 2 entries, interchanged the A and the D, and you put negative signs on the B and the C. Where's that come from? It comes from this formula that we had for adjoints. In fact, we probably derived this in that previous example. The determinant of matrix A is just AD minus BC, AD minus BC. So given the adjoint and given the determinant, we can state a formula for A inverse simply in terms of the entries of matrix A when it's just a 2 by 2 matrix, and we'll get this expression here. There's a chance, I only mention this because there's a chance you've seen finding inverses of 2 by 2 matrices before with this little formula. There's a pile of theory behind it, adjoints and determinants and all that stuff we've just recently done. I could shortcut, take this thing and multiply it by matrix A and see it really is an inverse. So you might have seen this if you've dealt with matrices before and you've dealt with inverse matrices before. You've seen this before, but there's a justification of it in terms of adjoints. A couple more things. Let's check and see if we want to do those. 36, I don't want to do that. It's lengthy. I'll leave it to you to read that. It's involved in terms of upper and lower triangular matrices. Oh, let's run through this one. All right. So a little proof. We'll run through this one. It's only one slide. It says, let A be an n by n non-singular matrix. Prove the determinant of the adjoint is the determinant of A to the n minus 1 power. All right. What do you know? You know relationships between adjoints and inverses. You know A inverse is 1 over the determinant of A times the adjoint of A. We've also seen that the determinant of an inverse is 1 over the determinant of the original matrix in that exercise, and we've used it at least twice. So let's take the fact that 1 over determinant of A is a determinant of A inverse, and the fact that we have an expression for A inverse. We know from this corollary that A inverse is 1 over the determinant of A times the adjoint of A. So let's take this stuff and substitute it in for A inverse. So we've got 1 over determinant of A equals the determinant of A inverse. Here's A inverse according to the corollary. All right. Now, what happens when we take this scalar, 1 over the determinant of A, and multiply it by the adjoint of matrix A? Does that affect the determinant of the result? Yeah, we've effectively taken the 1 over determinant of A, and I regret using this word, but we've distributed it over all the entries of A. It's not really distribution, it's how scalar multiplication works with matrices. But anyhow, you've taken the first row of A and you've multiplied it by the scalar. You've taken the second row of, adjoint of A and multiplied it by the scalar. You've taken all the rows of adjoint of A and multiplied it by the scalar 1 over determinant of A. You will recall, fingers crossed, that whenever you multiply a row of a matrix by a scalar, it affects the determinant of that matrix by a multiple of that scalar. We've multiplied every row of the n rows of adjoint of A by this scalar. Multiply the first row, produces a multiple of 1 over determinant of A. Second row, another multiple. On to the nth row, an nth multiple. So we've got 1 over determinant of A times itself n times, 1 over determinant of A to the n power, times the determinant of the adjoint of A. We didn't deal much with multiplying the row of a matrix by scalars. In fact, we kind of avoided it, but it was one of the properties, the scalar multiplication property, back in section 4.2 when we saw how row operations affect determinants. They produce these scalars. So this scalar gets produced n times. Why? Because the adjoint of A has n rows. So think of it like that, and that allows us to bring this outside. Now we've got the determinant of the adjoint of A. You like that? Well, that was part of the question. So we've got a formula now that reads 1 over determinant of A equals 1 over determinant of A to the n times the determinant of the adjoint of A. Let's cross multiply. Take this determinant of A to the nth power to the other side. You'll be left with the determinant of the adjoint of A, determinant of the adjoint of A equals determinant of A in the numerator on the other side to the nth power divided by determinant of A, comes from the denominator of that other side, just numbers, non-zero numbers, because we were told the matrix is non-singular, so its determinant is not 0. And we'll just cancel one of these determinant of A's in the numerator with a 1 in the bottom. We'll be left with n minus 1 exponent on determinant of A, and that was the claim. Determinant of the adjoint of A equals the determinant of A to the n minus 1. In hindsight, not a complicated question, undoable without all the determinant theory that we have as well, by the way. All it was really based on was that scalar multiplication property of how determinants are affected by multiplying rows by scalars, it turns out. That and our little formula for the inverse of A in terms of adjoints. So that should take care of this section. And let me stop sharing. Here we go. So that takes care of section 4.3 on determinants. In terms of looking towards a test, we'd probably do something involving using Cramer's rule on a 2x2 system of equation so you can illustrate your knowledge of it. I guess I could maybe have you find the inverse of a maybe 2x2 matrix using the formula for the inverse in terms of the adjoint. Much more than that is probably a little too much in a test-taking situation in terms of applications of this stuff. So there we go for section 4.3. Have a nice day.